Well, it's 2 o'clock, 2 o'clock in the afternoon on a Thursday afternoon. So a very well welcome to our webinar, our CHISA, EFCE, the Gruyter webinar. I think we have a good speaker today, but before I would like to introduce myself. I'm Willy Meyer. I'm the General Secretary of the EFCE, European Federation of Chemical Engineering. And I see we have already a lot of people joining in. So welcome wherever you are. Good morning, good afternoon, even good evening in the Far East. So, but before we start, I would like to draw your attention to our EFCE major event this year. And the major event is our ECCE conference, which will take place in Berlin. So, and I would like to give you some information about this. So, actually, you see here our conference series organized by the EFCE on the several years. So we start in 2013 here with our ECCE. Actually, the first one was in 1997. But during the recent years, we were in Barcelona, we were in Florence, and we intend to be in Berlin. I would love to welcome you all in Berlin for our European Conference on Chemical Engineering and our European Conference on Applied Biotechnology. Unfortunately, due to Corona and the pandemic, we could not do this year. Instead, we will have a virtual meeting here in 2021. But nevertheless, in 2023, we postponed the thing to Berlin again. And then we hope to welcome you then there for our ECC physically and in person. And in 2025, the conference will take place in Lisbon in Portugal. So the topics of the conference are, the headline is Engineering the Future, and we have, I think, very attractive things here, subtitles, Controlling Complexity, Engineering Processes and Products, and Life, and finding new routes to our products, our chemical products. And another thing is preparing for the future in the way of education, the way of training. How does digital developments involve e-learning, assessment, and these things? So I think it's quite interesting. And we have already fixed our plenary presentations for our September event in Berlin. There's Gyorgy Szekely, well known, of course, in this audience as the chief scientist in the Czech Republic. We have Melanie Maas-Brunner. She recently became CTO of BASF, a member of the board of BASF, Michael Doherty, the Dankwitz lecture, and Luisa Freitas dos Santos from Global Clinical Supply Chain from GSK. And so as I think we have very attractive plenaries here. So we have also satellite sessions here. They are confirmed. The Cape Working Party of the EFC will organize something. And we have Quality by Design. Artificial intelligence plays more and more important role in the issue, and also at our conference, of course. But you find all this information on the internet, so I invite you to go there. I can tell you that we have about 600 papers now, and the forecast is that we have 800 contributions here. So it will be quite a good event, quite the place to be for chemical engineers and biotechnologies in Europe. And I will invite you to be there. So, and having said that, I hand over to Karen, who will lead you to the program this afternoon. So, and Karen, please, back to you.
Thank you. Thank you. I will share my screen with you. So a warm welcome also from my side. My name is Karen Sora. I am Vice President, Science, Technology, Engineering, Mathematics at the Gruyter Publishers in Berlin for the German-speaking markets. I'm a chemical engineer by training, but worked in publishing all my life. So with Wiley VCH, Wiley, Springer, and now with the Gruyter for 10 years, building the international program. Why are we talking about the Gruyter? Because the Gruyter is strongly supporting these virtual events organized by the European Federation of Chemical Engineers, by DECHEMA, or by the Czech Society of Chemical Engineers, with the aid of our authors and our publications. The Gruyter is an independent scholarly publisher founded like 270 years ago. We have offices in Berlin, Basel, Boston, Munich, Beijing, Warsaw, and Vienna, 350 employees. We publish 1,600 books and 800 journals per year, We have over 20 international publisher partnerships, meaning that we have on our platform the ebooks from, for example, the whole Ivy League in the US. And we are also one of the largest open access publishers worldwide. So what does science, technology, engineering, mathematics at the Gruyter mean? It means we publish all formats in the subject areas of mathematics, in technology, which is computer sciences and engineering. And engineering here is electrical engineering and mechanical engineering. And then we also publish in the physical sciences, which is chemistry, industrial chemistry, chemical engineering, material sciences, and physics. And who is we? We is my colleague, Christine Smith, who will be the moderator during the lecture in this session, and myself. So why would one publish with us? Because we are fast, because we are personal. So the publishing company is big enough to follow technological developments, but also small enough to still be personal. And we publish in different subject areas and in different formats. So when you have content to publish, it would be ideal if you contact us so that we find the ideal type for your content, considering the market, considering the way you would like to structure your content. I wouldn't go into detail with this because I don't want to keep you from the scientific lecture. Just if you have content, contact us and we will be happy to discuss this with you. So how does it work? You would contact either my colleague Christine or myself, and then you submit a book proposal. We will provide you with a template, and you can write 150 to 350 pages. And the outcome will be a beautiful book, as you can see left-hand side. For instance, in the second row, the first one is the book published by Gyorgy Szekely, who will give the scientific lecture in a few minutes. There you go. All throughout the publication process, so from the very first idea through the manuscript generation and publication, and afterwards, we will be with you. We offer you support throughout the whole publication process. So simply contact us. We publish in the normal subscription mode, and this requires institutional customers. We also publish in open access, this provided there is funding, and of course also hybrid, meaning that only the content for which we had funding will be open and accessible to everybody. Aside from the beautiful books, we also have journals, and here I would like to point out in the bottom line, Reviews in Chemical Engineering, which would be interesting for this target group, which has an impact factor over 5. Or for instance, in the first row, Pure and Applied Chemistry, which is the journal of the Union of Pure and Applied Chemistry. We are their publisher. Also, we have an open access portfolio. Again, for this target group, I would like to point out in the top line, green processing and synthesis, or bottom line, nanophotonics, which has an impact factor over 7. So I would invite you to think of us if you would like to publish a book or in journals. The authors are important to us. And with this, I would like to hand over to my colleague, Christine Smith, who will be the moderator for the scientific section.
Thanks so much for that, Karen. So as Karen said, my name is Christine Smith. I'm an acquisitions editor with De Gruyter, and it's my pleasure to introduce the speaker today. Just before we get underway, a bit of housekeeping. We will have time at the end for questions. I ask that you please put all your questions in the Q&A section at the bottom of your screen, and then I will moderate them at the end. And yeah, feel free to add questions as we go through the webinar. Just we'll get to them at the end. That's completely fine. Okay, with that, I'd like to introduce the speaker today, Gyorgy Szekely. Gyorgy received his master's in engineering degree in chemical engineering from the Technical University of Budapest, and he earned his PhD degree in chemistry under the European Commission's Marie Curie Actions from the Technical University of Dortmund. He's held various positions at the University of Tokyo and the Imperial College of London before beginning his independent academic career. He was appointed a lecturer in chemical engineering at the University of Manchester between 2014 and 2018. And he also served as an adjunct faculty at Civita University between 2016 and 2019. Currently, he is an assistant professor in chemical engineering at the Advanced Membranes and Porous Materials Center at King Abdullah University of Science and Technology, or KAUST, and he's a visiting academic at the University of Manchester. He is a member of the Royal Society of Chemistry and was appointed a Fellow of the Higher Education Academy in the United Kingdom. His multidisciplinary professional background covers supramolecular chemistry, molecular recognition, molecular imprinting, process development, sustainable separations, waste utilization, nanofiltration, and pharmaceutical purification. Today, he will present a webinar on sustainable process engineering, continuous flow reactions, and separation, which will cover topics from his recent graduate textbook with de Gruyter, Sustainable Process Engineering, which was published in March of this year. And with that, I'd like to hand it over to our speaker. I'm really looking forward to the presentation.
Thank you very much, Christine, for the nice introduction. And thank you for the organizers to actually take care of this event and inviting me to deliver this seminar. Let me share my screen. Okay, can you see my screen and my pointer?
Yep, looks great.
Yes, okay, thank you for confirming. All right, so the title of this seminar today is Sustainable Process Engineering. And this seminar is actually based on a couple of chapters from this book that Christine just mentioned that we recently published together with de Gruyter. And today's seminar will specifically focus on continuous flow reactions and separations. Okay, so here you can see the outline of today's seminar. So I will give a brief introduction to KAUST and the AMPM Center where I work, and cover the research interests of my group, and then move into organic solvent nanofiltration and organocatalysis, and how these two different technologies and concepts can be integrated in a continuous manner. And one of the key takeaway messages from today's lecture is solvent recovery. So that's going to be another topic that I'm covering throughout the seminar today. And if we have time, then I will talk about the development of bio-inspired OSN membranes. Okay, so currently I'm based at KAUST, King Abdullah University of Science and Technology, which is based in Jeddah in Saudi Arabia, that you can see here on the Red Sea. And this is our university town. So on the left-hand side, you can see the Red Sea. So we are directly on the Red Sea. And on the right-hand side, we actually have the desert. So we live, work, and have fun on campus. Everything is happening here. You can see here the campus where we work, the community areas, town center, and we have an innovation cluster and the research technology park. We have here a couple of companies with R&D units that we closely work together with, such as Dow Chemicals and Aramco. Okay, so the university in numbers. KAUST is about 10 years old, so it's a relatively new university. It's a postgraduate university. We have students of about 1,000, and we are proud of our student to faculty ratio. We have 6 students and 1 faculty. That's the ratio, which is quite good. The majority of our students are PhD students that you can see here, and we also have master students. And we try to take care of gender balance. We have quite a lot of female students at this university. And at KAUST, we have over 100 different nationalities represented, and their distribution you can see here on this graph. Of course, the majority are from Saudi Arabia. Okay, so the teaching and the research is centered around three different divisions here at KAUST. And I work at PSC, the Physical Science and Engineering division. Within that, we have 5 different centers. And I work for the Advanced Membranes and Porous Materials Center, which is focusing on separation materials. Okay, so here you can see some photos of the university. This is our building. This is called Building 4 in the middle of the campus. And we are in this area within this building. This is another view of our campus. This is the same building where the membrane center is. And this is our library, by the way. Okay, so research areas, as I said before, we are focusing on organic solvent nanofiltration, catalytic membrane reactors, molecular imprinting from a materials perspective, and also from a chemical engineering process development perspective. And both aspects, the material science and the chemical engineering, are focused on the green and sustainable aspects of these subjects. So in a nutshell, the group is focusing on sustainable separations through a combination of polymer chemistry, material science, and chemical engineering. So we follow a bottom-up approach, and we start by developing new chemistry, which we turn into new materials, mainly membranes and adsorbents, and we also do surface modification of these materials. And then we develop chemical engineering processes to solve different industrial challenges, focusing either on pharmaceutical separations or petrochemical separations. And although these are very different industries, the common feature in them is that they are both using liquid separations for which membranes can provide a sustainable alternative nowadays. So why separation technologies and why separations are important? So separations are one of the most energy demanding operations. Here you can see the different types of separation units that are most frequently applied in different industries. And moving from right to left, the energy intensity is actually increasing. This is important because it means that it's not enough to obtain your products, but you need to make sure that you can purify them, for which you need solvents. Okay, and this brings us to the key point of today's presentation, which is solvent recovery. Why solvent recovery is important. And if you look at these separation processes, then almost exclusively all of them are actually requiring solvent for the separation to occur, which means that eventually you need to isolate your product and you need to do liquid separations. Okay, so why membrane? So before we go into the continuous membrane separations, then I'd like to introduce you to the basics of describing how membrane separations are actually carried out. So on the left-hand side, you can see a typical spiral wound membrane module. Okay, this consists of the membrane itself, which is responsible for the separation of your solutes, and it has other components as well. These are usually a flat sheet, and you stack them up, you roll them into a module, and you put them in the membrane housing. So this metal component here is actually the membrane housing, and within that you can see here the membrane module itself. So as for every separation, you need an input. So we have a feed stream, which is usually a crude product that enters the membrane module. And at the other end of the membrane module, you have 2 streams leaving the system. One is called the permeate, the other one is the retentive. The permeate stream is the one that went through the membrane. So usually this contains the solvent itself and all the impurities that are relatively small compared to your product. And the retentive stream is the one that is being retained or rejected by the membrane. So again, this has the solvent with the solutes that are large enough not to go through the membrane. And this concept is also represented in the bottom right corner of the slide. You can see that you have a feed stream here with smaller and larger species dissolved. And in the retentate, the rejected molecules are collected. And in the permeate, you're going to have the small impurities and the solvents. So the two key components that I keep mentioning here is solvent and solute. So we need a descriptor how effectively membranes can separate solvents and solutes, and how the transport is happening through the membrane, for which we have two different concepts. We can talk about flux and permeance, which describes the solvent permeation through the membrane. And then with respect to the solute, we have rejection. Okay, so the solvent throughput is expressed as liters of solvent passing through the membrane over a unit membrane area in a given time. So this is flux. And if you normalize it by the applied pressure, then you get the permeance. And this is giving you an idea about how fast the separation is happening through the membrane. Whereas when you look at the solute descriptor, which is the rejection, this gives you the selectivity between compound A and B, how well the membrane can separate two different compounds. So the flux and permeance is more about how fast the separation is happening, while the rejection is describing what is the selectivity during the separation. And the rejection is calculated basically it is the ratio of the permeate concentration over the retentate concentration. So we have a high rejection when nothing is going through the membrane. Let's say you have 100% rejection when the solute is large enough not to penetrate through the membrane. You have 50% rejection when half of it can go through and half of it not. So in that case, we have no selectivity. And we have low rejection, such as 0% or a couple of percentages, where the majority of the solute is ending up in the permeate stream going through the membrane. So you could ask which one is more important, the retentate or the permeate stream at the end of your process. And it depends on what you want to do with your membrane. So in continuous membrane separations, you can concentrate your product, which means that the product should be large and is going to be retained by your membrane, and the solvent will pass through the membrane, eventually leading to a retentate that is highly concentrated in your product. And what's the advantage of using membranes when you could do distillation? So distillation does essentially the same thing. You have a product, you distill off your solvent, and you end up with a concentrated product stream. But in certain industries, such as the pharmaceutical manufacturing industry, often you have intermediates and final products which are extremely sensitive, for instance, to heat. And in that case, you cannot apply distillation, or you need to apply vacuum distillation with high energy intensity. And in those cases, membranes can provide a sustainable alternative because they don't need phase changes, and they only use basically 1 or 2 pumps at a relatively low pressure to drive the separation. Okay, so within membrane separations, we can classify them based on the transport phenomena that happens through the membrane. You can classify them based on the pore size of the membrane, which is one of the most common classifications. And within that classification, one category is nanofiltration. And today I'm going to focus on nanofiltration because this, this group of membrane separations is focusing on distinguishing molecules with molecular weight of 100 to 2000 Dalton, roughly, which falls perfectly into the regime of the pharmaceutical industry. In other words, with nanofiltration, you can separate the impurities, which are usually small, around 100 Dalton, from the product, which are often 500, 1000 Dalton. And Nano filtration was originally developed in water and aqueous separations, but nowadays we can perform nanofiltration in organic solvents. And we can not only perform these separations under harsh environments, such as organic solvents, but with the recent development in material science, nowadays we have new membranes that provide better reproducibility, tighter and better pore size distribution, more stable membranes, faster filtration, and more robustness. And these latest inventions, they allow us to develop new type of chemical engineering separation processes and to couple OSN with, or nanofiltration processes with other type of unit operations, such as continuous flow reactors. So here you can see a plot that shows the rejection of the solutes as a function of molecular weight or the pore size or pore radius that you can see here on the x-axis. And this straight line here, this vertical line, shows the ideal separation that membrane scientists really look for, because this means that you have a very low rejection, virtually a 0% rejection for a given solute, and another solute which is slightly larger will have 100% rejection. Okay, this is the holy grail of membrane separations, where you have an extremely high selectivity between two solutes with a very small difference in their molecular weight or size. But in reality, we don't get these separations instead, and these vertical lines, but instead we have these so-called cutoff curves that you can see here as dashed lines. And these cutoff curves and their shape gives you an idea, a rough estimation, what are the different solutes that you can separate with a given membrane. So let's say with the first line or first curve, with an MWCO, this is the molecular weight cutoff of 100, can separate solutes that are smaller than this and larger than this. Okay, and the sharper the curve, the better and the higher the selectivity you have. And this is the value that is usually used to describe membrane separations and to choose the right membrane for the right application. So as I mentioned before, nowadays we have tighter membranes, which means that these values are decreasing. Okay, and we can separate solutes that are relatively small, and they have a small molecular weight gap between the two solutes to be separated. Okay, so this is the basics of organic solvent nanofiltration. So now I would like to show you the very first example, which is about the coupling of a continuous flow reactor with a continuous flow membrane separation, nanofiltration in particular. So I'm going to take you through the method development from scratch, basically. So here you can see the modal reaction. You have a substrate, you need a catalyst, you have a reagent, which is nitromethane in this case, and this is a Michael addition, where you end up with this product. You can see that the molecular weight of the raw material increased from 208 to 269, and we have a reagent which is relatively small. It is 61 Dalton, and the catalyst that was applied in this particular case study is actually there were two catalysts that we were looking into. You can see the structure on the left hand side here and the other one on the right hand side. So this is the amber list and the amber light resins that are commercially available. These are solid state supported catalysts. And the first step was to optimize the continuous flow reactor. And we were interested in the conversion of this reaction under different temperatures that you can see here. So if you start increasing the temperature, then you're going to have you can achieve higher conversion in a quicker time. But what we observed is that these two catalysts, they deactivate at given temperatures. On the left-hand side, this A21 catalyst deactivates above 50 degrees Celsius, and the IRA67 catalyst deactivates above 60 degrees Celsius. So although we achieved virtually 100% conversion in a relatively short time, over longer time, the catalyst started to degrade. So we decided to actually decrease that temperature. The second step for the optimization was setting the substrate to reagent ratio, okay, the molar equivalent. Here you can see that we explored 1:5, 1:4, and 1:3 equivalents. Of course, the higher the equivalent, the quicker the reaction and the higher the conversion. However, the ratio of these two is basically 1:1 in a sense that one substrate will react with one reagent, forming 1 mole of product. So whatever you're using in excess here is going to contaminate your product stream, and it's going to make your separation and purification of your final product more difficult. So of course, it would be ideal from a conversion perspective to use 1:5 ratio, but then you end up with 4 equivalents of remaining reagent that you have to remove from your product stream. So you have to compromise the equivalent and the ease of purification. And this is where membranes come into the picture, because in this particular reaction, the reagent is small and the product is much larger. Therefore, we could apply size exclusion membrane separations to end up with a pure product stream and another stream which contains the reagent, which hopefully can be actually recovered and reused. So this was the hypothesis of this particular work. And here you can see the actual process scheme on the left-hand side. So without going into too much details, I just want you to understand the concept behind it. So what's happening here, you have a continuous feed stream on the left. You need a high pressure pump, okay, that is going to provide the pressure for the membrane filtration. And let's just ignore the dynamic mixing chamber for a second. Imagine that you're using one pump, it goes into your flow reactor. In this particular case, a PEG bed reactor was used. As I said, we have a solid resin catalyst filled into this PEG bed. Here is where the conversion happens. So virtually we can achieve 100% conversion. Then you have your crude product leaving your reactor, which should divert into a nanofiltration rig. And within the nanofiltration rig, you have your membrane itself that you can see here at the bottom. And the second component is another pump. This is a recirculation pump that you can see here, which helps to avoid the concentration polarization during the continuous filtration. And as I said before, the membrane will split your feed stream, your crude product, into 2 streams. You're going to have retentate on the right-hand side, and this is where your product will end up because that has the larger size, and your impurity, which is the unreacted reagent in this case, and your solvent will end up in the permeate stream that you can see here in blue. So in this case, we can take the permeate stream and recycle it back into the reactor. Okay, so this allows us to actually minimize the solvent consumption of this production unit, and it also allows us to recover the excess reagent. So as we said before, if we maximize the excess of the reagent, then we can obtain 100% conversion in a relatively short time. So this is beneficial, but the issue was the excess 4 equivalents of reagent, what to do with that. So now with the means of membrane technology, you can recycle at the same time the solvent and the reagent back to the flow reactor. So this means that there is a startup period for this type of unit operations, because at the beginning, the conversion needs to go up. The outlet stream of your reactor needs to reach steady state. Then, as soon as it is fed into the nanofiltration unit, which is at the beginning of this operation, only has a solvent inside, again, the concentration needs to build up. You need to reach steady state, and then you can close this loop and divert the permeate into the mixing chamber and back to the flow reactor. At that moment, when you start recycling the solvent and reagent, then you need to adjust the concentration in your feed stream to ensure that the inlet of the reactor is kept constant. Okay, that's the only way to actually keep this whole continuous operation on the steady state. All right, so now let's look at the concentration profile on the right-hand side. So what I just explained on the process scheme, we're going to see how that translates to the actual concentration profile on the right-hand side of this slide. So we are interested in the concentration of the product and the reagent in the retentate and permeate streams. So what you can see here is that the product concentration over time increases and reaches a plateau, and then we obtain a steady state in the retentate stream. Parallel to this, the reagent concentration is also building up in both the retentate and the permeate. Okay, and then again, we reach steady state. And we were performing these reactions in continuous flow over 6 weeks, okay, without loss of any noticeable loss of catalytic activity. So we managed to actually keep the ton and TOF numbers relatively high. So what is TON and TOF? These are the turnover numbers and the turnover frequency. So the turnover number gives the number of moles of the desired product that forms over the surface area of the catalyst, or the number of catalytically active sites. And if you relate that to the time, then you get turnover frequency. We obtained the productivity of 3.75 gram per liter per hour and the product purity of 92%. Okay, so why is the product purity only 92%? The membrane can retain your product at, let's say, 100%, which means that all the product ends up in the retentate stream. However, the impurity, the reagent itself, has a rejection of about 20 to 30% in most cases. And this means that there is a split between the permeate and the retentate streams. So although the majority of the reagent is recovered and goes back to the inlet of the reactor, some of it will end up in the retentate stream. And this is the one that is contaminating the product and brings down the product purity to 92%, which is still relatively high. Another key concept here is actually the concentration of the product. So we've talked about already two advantages of coupling a continuous flow reactor with a continuous flow membrane separation unit, which is solvent recycling, in situ solvent recycling, and in situ reagent recycle. But another advantage is that you're immediately concentrating your product. So if you look at the flow rate of the retentate here, you can see that it was 0.091 milliliter per minute, while the permeate flow rate is 0.909 milliliter per minute. Okay, so it's about 10 times higher, the permeate flow rate, than the retentate flow rate. So when you have your feed stream going into the membrane separation unit, then essentially 90% of the solvent ends up in the permeate, and 90% is recovered and recycled back to the reactor. And the other 10% ends up basically keeping the product in solution. And this means that you're concentrating your product about 10 times, okay, which is beneficial because at the end of all of these operations, you're going to obtain a solid, crystal, or an oily product that you want to concentrate up anyway. So in one go, you can do three things: solvent recycle, reagent recycle, and product concentration, and actually product purification at the same time. Okay. At the beginning of this example, I mentioned that you need to wait until you reach steady state in your nanofiltration unit and your reactor to close the loop and start recycling. Okay, and that has actually quite a lot of effect on different aspects of this process. So if you look at the concentration profiles, you can see that the product concentration reaches a relatively high concentration of about 27 gram per liter, and this takes a longer time. So equilibrium is reached somewhere around here, which is between 1 to 2 days. However, when you look at the reagent concentration and how this profile looks like, then you reach equilibrium in a much shorter time. Only within 2.5 hours, you can reach equilibrium for your reagent in both the retentate and permeate stream. And the reason being, you have a much lower concentration, eventual concentration to reach. Okay, and I'm going to get back to that point later on because this will be quite important when we start assessing the sustainability of this particular example. Okay, so I wanted to show you a rendered image of our unit that we have in the lab. We actually have 2 of these units, and they have 2 PET process analytical technology implemented. Here, this is an inline FTIR, and this is an inline NMR. And here you can see the membrane separation unit and the reactor, and it's the same in both sides. So the system can be a thermostat, and you can set the temperature here using these thermostats. And here you have the membrane cells for the separation. You have a high pressure pump here, and you have down here below the bench, you can see the recirculation pump, and this is the pump head sticking out. The flow reactor itself is somewhere in the middle. Again, the majority of it is placed underneath the worktop. So this is a closer look at the same system. So these are the membrane cells that you can see here. These are operated at room temperature, and you have these in an oil bath, which are operated at any temperature that you want to set. These are the pump heads of the pump that is below the bench, responsible for the recirculation of the retentate loop that you can see here. Here is the permeate collected. So this is basically the stream that is going through the membrane. And here you can see the retentate stream. So this is the one that is not going through the membrane. So eventually your product will end up here, and your impurities will end up here. And the feed is basically this part here. And this is the top of the flow reactor placed under the bench. And this can be connected either here as the feed, or it can be connected to the other membrane system. Okay, so just to wrap this up, you have the high pressure pump, which is under the table here. You have the recirculation pump, which you can see here. The membrane itself is placed in these cells. The reactor and reactor housing that you see here is in the middle here. Okay, so from an operation perspective, it's very important to do a sensitivity analysis and understand how the different process parameters are affecting the outcome. So what is the outcome that we are interested in this particular hybrid reactors. The product purity, the solvent consumption, productivity, and equilibrium time. So these are the parameters, the output parameters that you can see on the y-axis of these plots, while on the x-axis we have the variables that we can change. These are the process parameters that we have usually control of to fine-tune the reaction, and also to check how sensitive your overall system is when there is a fluctuation in any of these parameters. So these parameters include the membrane loop volume over the membrane area, includes the product rejection. So membranes over time can age, and the rejection of the solutes and their selectivity can change. So this is reflected in the product rejection or the reagent rejection. Then we have conversion. If something happens in the reactor and the conversion changes, then what is the effect of that? Or what is the effect of the retentate and permeate flow rate ratio? So as I said before, when you set the retentate and the permeate ratio, then that's going to determine how much you're concentrating your product up. So in our particular case, it was set to 0.1. So these arrowheads in each of these plots actually show the optimized condition that we were operating at. So in this case, it is kept at 0.1, which means 10% retentate, 90% permeate. And the last parameter is the excess of the reagent. As we discussed before, if you maximize it, then you're going to have a higher conversion. However, that's going to have an effect on the purity. And this is represented in this plot. Okay, so you can see, I'm not going to go through all of these variations, because that would take by itself 1 hour. But what you can see here from these 6 plots is that it's not that obvious to judge which parameter will have what effect on the different outputs. And some of them are linear, others are not. So it's important to perform a sensitivity analysis and see how robust your process is. And in these cases, when you apply a hybrid process, reaction separation combined, then it's a good idea to run the sensitivity analysis in a way that you check the effect of one unit operation on the other unit operation, such as we did in this particular case. Because when you're recycling, when you do in situ recycling, and you feed back the output, the permeate stream or retentate stream of your membrane unit back into the reactor, then whatever happens in your separation unit with your membrane, that's going to have an effect on your reactor. And whatever happens in the reactor will have a significant effect on the membrane separation. Okay, so on the right-hand side, now you can see the E factor and the carbon footprint. So this is basically the result of the sustainability assessment of this hybrid process. So we were interested in 2 different cases that is represented A and B. So A is in situ solvent and reagent recovery with and without. So with and without the solvent recovery on the E factor, and the other one is the same but on the carbon footprint. So what you can see is that the E factor, which is kilogram per kilogram, so that gives you the amount of waste generated to obtain 1 kilogram of product. So if you don't do solvent recovery, solvent and reagent recovery, then you're going to end up with a waste generated of about 300 kilogram per kilogram of product. And that sounds like quite, high number, right? 300 kilogram of waste to obtain 1 kilogram of product. But actually it's not that high still. So in the pharmaceutical industry, the E factor value is usually above 100 and then can reach easily hundreds. Okay, and the reason being is that pharmaceuticals have to be high quality, high purity, and usually when you need to achieve high purity, then you need to do more and more purification, which leads to product loss and leads to the use of excessive consumables. And therefore, it's very important to minimize the waste generated in the pharmaceutical sector. And as you can see here, by applying solvent and reagent recovery in situ, we can reduce the E factor, in other words, the waste generation, by 91%. Okay, so the E factor takes into account the catalyst waste, the membrane waste, the solvent waste, and the reagent waste. And if you look at the carbon footprint, that incorporates, this is the carbon footprint, it incorporates the E factor, so all the waste that you generate during your process, and it also takes into account the energy that is needed for the recirculation pump, for the high pressure pump, and for the thermostat that you're using to control your reactor. And if the energy is also taken into account, then the sustainability assessment changes. So if you look at the carbon footprint, then the obtained reduction is much more modest. It's only 19% compared to the 91% reduction in the E factor. So why is that? Because we are reducing the waste, but there is a huge energy consumption associated with the use of the thermostat. Okay, this is the main contributor to the carbon footprint. Okay, so in this case, you can see, if you look at this overall assessment, that in terms of waste generation, the implementation of a continuous membrane separation unit will have a significant effect on waste generation and its reduction, while the overall carbon footprint is not going to be affected that much, because that is dominated not by the waste, but by the energy consumption. And it's worth to mention that the energy consumption is not related in this case to the energy requirement of the components of your separation unit, which is the two pumps, but actually the thermostat, which is related to the operation of the reactor. Okay, and this is a rough estimate that you can see here, how the energy was calculated. And in a real industrial scenario, of course, there is heat that you can recover in a company, and that's going to significantly reduce your energy consumption for your thermostat. Okay, so which means that the contribution of the waste will increase, and then this reduction will be larger than what is shown here in terms of relative percentage. Okay, so another important point related to solvent recovery is actually the need for solvents in general during the purifications, which I already mentioned earlier. So here you can see the solvent consumption in cubic meters, and here the impurity removal. So what you can see here is that when you start increasing the purity, when the requirement for high purity arises, especially in pharmaceuticals, where we are talking about 99% plus purity, then the solvent consumption significantly, rapidly shoots up. Okay, and this is why it's very important to incorporate a solvent recovery unit when you need to obtain high purity products, because then you're going to have a high solvent consumption that relates to a high E factor, and it has a lot of implications on your overall process. So it's a good idea to start implementing solvent recovery. Okay, so what are the options? On the left-hand side, you can see a conventional unit operation scheme for solvent recovery, where you have your own process here. This is basically a black box, and then you collect your spent solvent. Then you send it to spent solvent holding, where you collect it after each batch, and eventually you do the distillation from there. And then you end up with a clean solvent holding. Again, from there, you feed into a process side clean solvent that you can use for your actual process. On the other hand, what I'm proposing here is to use in-situ solvent recovery, which means that you don't need any of these represented in blue. What happens is that you have your own process here, the black box, and within that, you have your, let's say, your membrane separation unit that allows you to in-situ recover your solvent. And this is what you can see here. Let me go back to the process scheme. This is what you can see here. So you have your reactor, and immediately the spent solvent goes into a continuously operated nanofiltration unit, where the permeate is diverted back to your flow reactor. Okay, so you don't have to store the spent solvent, and you don't have to distill it either on site or off site, and then store it again, transport it, and then feed it back to your flow reactor or any reactor. But in this particular case, it goes automatically, this whole recycling. Okay, so this also significantly reduces the footprint of your manufacturing. Okay, some actual numbers. So here you can see we are comparing without solvent recovery and with solvent recovery on the left hand side and the right hand side of the slide. And we are looking at the energy consumption, waste generation, and carbon footprint. So this table is basically showing the actual breakdown of the numbers that were used to generate the plot that I showed in the previous slide. And you can see here that the energy consumption, the thermostat is the main contributor. For the waste generation, it's the solvent. And these are basically just the actual values, so we don't have to go through that now. Okay, so one question that arises is how to convert all of these different informations that we gain, such as the waste generation and the energy consumption, into carbon footprint. Okay, and for that you have different options. So EcoInvent and also CCOG were developed. These are LCA life cycle assessment based evaluation tools developed by ETH Zurich and the University of Manchester, and they provide these platforms. You can go online and you can find out what is the carbon footprint or CO2 equivalent of a given process, of a waste, of any type of activity. It can be transportation, it can be a food product or cosmetics, and so on. It takes into account, just to get back to the original topic, which is solvent recovery and continuous operations. In our case, we can put in the solvent that we are using, and it will calculate an equivalent CO2 behind that waste solvent that we generate. It takes into account whether the solvent is chlorinated or not, and so on. Okay, and some of these calculations and concrete examples, green metrics analysis, is actually presented in this book that we recently published. So if you're interested in sustainability assessment of these type of processes, then I recommend our book. Okay, and the final thought on this particular example that we've been discussing is what is the cost of adding or coupling an OSN or a nanofiltration unit to your reactor. Of course, it's an investment. It's a capital investment, and you also need to invest in energy, consumables, and so on. So if you take all of this into account, then you can generate this plot on the left, which shows the carbon footprint of the process over generated kilogram of product as a function of processing time. So we are talking about continuous processes. So the longer you operate it, the more sustainable and more efficient basically your overall process becomes. And what you can see here is that if you don't have solvent recovery, then you have a given carbon footprint to operate it, and that is more or less stable. It is, I think it is slightly increasing actually over time, but it's not a significant increase. But when you look at the cost of the solvent recovery unit, basically the membrane unit, then at the beginning of your process, because of the additional investment, you have a very high carbon footprint. But as you start processing your product and you start recovering your reagent, start recovering your solvent, then this carbon footprint goes down. And the more you recover, essentially, the more you run your reaction, then the carbon footprint reduction becomes larger and larger. So eventually, you're going to end up with a lower carbon footprint than without solvent recovery. And at steady state, these two values are basically the ones that I was presenting in the previous slide. Okay, and one final thought about, it's a more general comment. Here you can see a plot that shows the top solvent waste generated in the US. This is not very recent data. I think this is based on this ranking of solvents is based on data which is already about 5 years old. But nonetheless, this graph here, or this bar chart, shows the potential of incorporating a continuous membrane separation into your process and how much carbon footprint reduction you can achieve. So different solvents, as I said before, will have different carbon footprint equivalents, and usually chlorinated or halogenated solvents, they are more harmful from the environment, so their associated equivalent CO2 when you incinerate these solvents is much higher. So when you take all of this into account, how many carbon atoms they have and so on, then you end up with this chart. And this shows that if you recover your solvent with the process that I was explaining, then you can achieve about 90% CO2 footprint reduction for methanol, a more significant one for dichloromethane or chloroform, and so on. And this ranges between, in the top, I don't know how many solvents we have here, maybe 10 solvents. So in the top 10 waste solvent generated, you can reduce the carbon footprint by, let's say, 17 up to 31%, which is quite significant. Okay, so we still have time. So I'm going to introduce you to another continuous aspect for integrating continuous reactors with continuous membrane separations, which is an organocathetic membrane reactor. So what we have seen so far is the use of a continuous flow reactor where you run a heterogeneous catalysis, and then you couple it with a membrane reactor, and then you recycle your reagent and solvent. So this requires 2 unit operations. And if you still remember all the plots and all the different data shown for the sensitivity analysis, then that tells you that this is a relatively complicated system. However, what if we could do that in a single unit operation? Okay, and to do that, you need to have a membrane that has a catalytic activity. So that combines the 2 concepts, the reactor and the separation unit. So in this particular case that you can see here represented, this is a membrane material that has a size exclusion feature, so you can do separation with it, but at the same time, it also acts as a catalyst. So you can perform the reaction of A plus B, giving you, your product, which is C. This means that you don't need 2 unit operations, you only have 1. You can significantly reduce the energy consumption, and you can also reduce the actual footprint in your laboratory or in your manufacturing site. Okay, so due to the lack of time, I'm not going to go through these slides in details, but I'm going to try to give you an overview of the concept. So membranes are usually manufactured by phase inversion, which means that you have a dope solution that requires a polymeric material. You prepare a thin film out of it, and then during the phase inversion, you place it into a non-solvent, usually water, and you end up forming a solid film, which is actually the membrane itself. So in this particular case, you can see here the polymer, which is polybenzimidazole, and then you can do surface modification of this membrane, and you can attach a known catalyst onto the surface. So in this particular case, we did click chemistry to covalently anchor this asymmetric organocatalyst onto the membrane surface. So at this moment, we not only have a membrane, but we have a membrane that can do catalysis at the same time. I'm going to skip all the slides about the chemical and material. Actually, it was one slide. This represents how we characterize this membrane. So let's focus on the chemistry and chemical engineering aspects. So again, we turn to Michal addition and Michal addition. And since the catalyst that we anchored onto the membrane, it's an asymmetric catalyst, which means that when you react your substrate and your reagent, that you're going to end up with an enantiomerically pure product. Okay, so here you can see the modal reactions on the left-hand side. We tried many different reactions, 1 to 8, with different functional groups. These are the entries represented here. And we performed this catalytic reaction in 3 different ways. We used the original small molecular catalyst dissolved in a solvent. Basically, that is a homogeneous catalysis. And in option B, we used the membrane catalyst in a stir tank. Okay, so in that case, the membrane only acts as a polymeric anchor for the catalyst, but it is not being used as a membrane, and the size exclusion feature is not being utilized. In option C, which was our ultimate goal, is to use it as a membrane reactor, where we place the membrane not in a stir tank, but into a membrane cell, apply pressure, and then we have both tangential flow at the surface of the membrane, and you have perpendicular flow going through the membrane, and therefore we intensify the mixing and the chances for catalysis for the substrate to make the reagent on the catalyst itself. Okay, so now let's look at the results, and there are 2 main parameters that you're interested in these particular type of reactions or operations. One of them is the yield, okay, the product yield, and the other one is the enantiomeric excess. So how selective your reaction is, how much desired product you get, either the R or the S enantiomer. And the different colors represent the different scenarios that I just explained to you. So bottom line here is that you can maintain high enantiomeric excess, so high selectivity with the membrane reactor. Okay, in some cases it was compromised somewhat, but it's still a relatively high value. And when you use your membrane as a solid support, then usually there is a drop in the yield. Actually, in all the cases, there is a drop in the yield, because here we are moving from homogeneous to heterogeneous catalysis. But if you apply it as a membrane and you apply pressure and you have flow through, not only a tangential to the surface of the membrane, but through the membrane material, then you can actually increase the yield back to the original value, or in some cases, you can even achieve a higher yield than with the original catalyst in homogeneous catalysis. So these results were very interesting. Okay. All right, so after obtaining these experimental results, we wanted to check whether there is any molecular explanation, molecular level explanation for the improvement of the catalytic activity. And then we turned to DFT modeling of the whole system, including the polymer backbone, which is basically the membrane, and then the covalently anchored catalyst. And again, the conclusion here is that what we observed, that the presence of the polymeric chain does not have an adverse effect on the catalytic activity, but quite the contrary. And what happens is that the combination of the polybenzimidazole with the catalyst is actually helping to adjust the angle of the substrate and the reagent and bring them closer to each other, which is beneficial for the reaction. And this is what you can see here. So it was very nice to see how the experimental results, they come hand in hand and they are aligned well with the modeling. Okay. So optimization of these systems is not easy. We looked at the sensitivity analysis, and you can see how many parameters are there to change and to take care of. And in this particular case, we turned to design of experiments. We used the software called Modal 11, and we used the central composite phase with 30 runs. And here you can see these contour plots that show the optimization. And we were focusing on the membrane aspects and optimize the applied pressure and the recirculation flow rate and the reaction time. So of course, you want to have high conversion. This is what the color scheme represents. But at the same time, you want to minimize the pressure, you want to minimize the reaction time and the recirculation, which all require energy and eventually compromise your profit margin. Okay. Okay, I'm going to skip this part and move on to the process itself. So here you can see that you have a stir tank, and then this is connected to the membrane unit. This has the catalyst inside. So don't forget that this is a membrane with a catalytic activity. So what happens here, initially you have reagent and substrate that turns into the crude product. And then you use the size exclusion feature of your membrane to purify your product. So here you end up with a purified product at the end. And what happens in the permeate after the filtration is that you divert it into a second stage of a membrane unit. So we are talking about a membrane cascade. And in this second unit, you can recover your substrate in the retentate, and at the same time recover your solvent and feed it back to the original process. Okay, so again, we can incorporate many different objectives in this single unit operation, which is solvent recovery, substrate recovery, and catalytic activity at the same time, and product purification. Okay, so this is just a reminder of how this experimental setup actually looks like. You have the reactor here, which represents the previous case where we had the PEG bed. And in this case, basically this part is not used, but you only use the membrane cell where the separation and the catalysis happens. Okay, this shows the concentration profile where in the first stage you have catalysis happening, and once you have reached the desired conversion, then you can switch to the separation after the catalysis. So basically, this is done in a staged manner when you have a catalytic membrane reactor. Okay, so again, we looked at the sustainability assessment of the system without the solvent recovery unit, with solvent recovery unit, and the recovery and reuse of the substrate. And then in this case, we also have a third scenario where we recover the solvent, but we do not recover the substrate. So why did we introduce this third scenario? In the pharma industry, you need high purity. And if you keep reusing your substrate, which is not 100% pure, then eventually you're going to start building up impurities in your product stream, and that's going to compromise your overall purity and performance. So in practice, it is preferred to discard your substrate or use it for other purposes, but not feed it back into the same manufacturing line. And therefore, the preferred option by the industry is case 3. However, to be optimistic, and in case you want to recover your substrate and reuse it, then you can go with case 2. And the worst case is if you don't recover anything, this is without solvent recovery. So just to focus on the main numbers in this table, you look at the E factor, again, that's the waste generation. You have a significant waste generation of 141 kilogram per kilogram. If you recover everything and reuse your substrate, it goes down significantly, as you can see. But if you decide not to recover the substrate, only recover the solvent to be on the safe side, then it goes down from 141 to 9, and this is still a very nice reduction in your waste generation. And the trend is somewhat similar with the equivalent CO2, basically the carbon footprint. You have a large carbon footprint initially if you don't do any recovery. And then if you recover everything, then it goes down to 16. If you don't recover the substrate, then it's 34. Okay, so now that I'm getting near the end of the presentation, I wanted to show you very briefly, I think it's a single slide, another approach. So far what we have seen is that in the first case, we applied continuous flow reaction. We coupled it with a nano filtration unit, okay? And the reaction was heterogeneous catalysis performed in a packed bed reactor. Then we had the membrane unit, and then we recover what we recover. In the second case, we only had the membrane unit, which did the separation based on size exclusion, and also did the catalytic performance because it was the catalyst itself. And now in this example, what you can see here is that you have a coiled tube plug flow reactor, and then coupled to the nanofiltration unit. And we are recovering the catalyst, and we are recovering a solvent in this case. Okay, so before we were recovering reagents and substrates and the solvent, and in this case you can recover the solvent and the catalyst. Okay, so what is the main difference between these units? So in the first one, here in this housing, we had a packed bed reactor, and now we have a coiled tube plug flow reactor, which means that in the first case was a heterogeneous catalysis, and this one is a homogeneous catalysis. So in this case, you don't have any solid supported catalyst, but you have a catalyst that is in solution. Okay, so if it's in solution, it means that it's going to end up in the nanofiltration unit. Okay, and if you want it to be recovered, then it needs to be large enough not to go through the membrane and end up in the permeate, basically decreasing the purity of your product, contaminating it, in other words. And to apply this concept, we need to turn to different tricks. Okay, so with the heterogeneous catalysis, you're using a solid supported catalyst, so the solid can be is not contaminating your product, and it's not going inside the membrane unit. In this case, if you take the original catalyst that you can see here, it's relatively small. It can have more or less the same size as your product, which means that you cannot use membranes to separate the catalyst from the product. So what you want to do is increase the size, because the product is fixed. So what you can play around with is the catalyst. So if you increase the size of your catalyst to make it much larger than the product, then you can apply membranes, size exclusion membranes, to separate these two. So what you can see here is the catalyst anchored to a soluble support in this case. Okay, and this example represents the use of a cyclodextrin, okay, which is a natural material which is very cheap. It's large, and that's the objective. That's the main feature here, that we need to be large in terms of size. So we covalently attached an organocatalyst onto it, and then we end up with a supported catalyst that is still solution processable. So in this case, we can use a coiled tube plug flow reactor, and then downstream of this reactor, we go into the membrane separation unit. We have the catalyst that is large, so that can be recovered in the retentate with the solvent, and the product goes through the membrane and ends up in the permeate. What we observed in this particular case is that the increase of the concentration of the catalyst during the nanofiltration unit operation results in the precipitation of the catalyst, and I think also the product concentration was relatively high, and because of that there was some precipitation. So you want to avoid that in your nanofiltration unit, because that's going to clog your membrane. So you need to choose a very open membrane. In this case, we choose the membrane with a cutoff of 900, so it's a relatively open membrane. And we had to increase the temperature. So here you can see that the nanofiltration is actually performed at 50 degrees Celsius. Okay, and this trick allowed us to keep everything in solution without clogging the membrane itself. Okay, so we can obtain 100% catalyst recovery because we have a large catalyst which is not going through the membrane. The enantiomeric excess was 99%. So again, the catalytically active site of this organocatalyst was not affected by the anchoring to the cyclodextrin. We obtained 98% product purity and demonstrated a stable performance over 18 days of continuous operation. Okay, and this is the last example that I'm going to go through, which is not about the attachment of or coupling of a membrane unit with a reactor, but in this particular case, membrane unit was coupled to a temperature swing adsorption unit. Okay, so basically we are coupling two separation units with each other, both in a continuous manner. So this work was done in collaboration with a Turkish partner. In Turkey, they are one of the largest manufacturers of olive oil. And the first step is basically harvesting the olives. Okay, and during the harvest, they end up beating the tree and the leaves are falling on the ground, which eventually gets collected and used as an animal feedstock. So in other words, this is an agricultural waste. However, not only olives themselves, they contain a lot of pharmaceutically relevant and biologically active compounds, but also the leaves are full with antioxidants and many different compounds that are of high value. So we wanted to demonstrate that it's possible to extract these antioxidants from this complex mixture, this agricultural waste. So we developed different imprinted polymers, and it's important that these are imprinted because they give you high selectivity. Okay, so the concept of imprinting is shown here. Briefly, you have the compound of interest and you create this polymer matrix around it, and then you can remove the template and you end up with this polymer that has these cavities inside that are complementary in terms of size that you can see here, chemical functionality, and topography of the original molecule that you used as a template. So therefore, the selectivity, this material can selectively extract out your antioxidant from the waste stream. Okay, so here we focused on oleuropein, which is the antioxidant, and we use the functional monomer that you can see here. We developed different polymers and used different green solvents and ended up optimizing this process. So it consisted of adsorbent screening, solvent screening, and we ended up using ultrasound for the extraction from the leaves into the solution. Okay, so this is the very first step. Okay, so again, without going into details, you can look into the adsorption isotherms to understand what is the effect of the temperature on the system, which is going to help you to develop the adsorption and the desorption process. You look at the adsorption kinetics, which is going to determine how quickly you can swap or do the swing between the adsorption and the desorption. This is done in batch. So then you have to convert this data into flow. So you need to pack a bed with your adsorbents, and then you can get breakthrough curves describing your system. Eventually, you can look at the utilization of the column capacity and maximize it and minimize your product loss. So after all of that, basically you optimize your adsorption and your desorption conditions. Then you can build your system and connect it to your nanofiltration unit. Okay, so what you can see here on the left-hand side is that you have the leaf extract as a result of the ultrasound. Then you pump it through your adsorption column, okay, in the first place. Then your valuable compound is extracted onto the column, and your waste ends up in your nanofiltration unit, okay? where you can concentrate it. Okay, so that's going to be your retentate. You have a concentrated waste stream. And at the same time, what goes through the membrane is a relatively pure solvent that can be recycled and reused in this process that you can see here. It's being collected here. And parallel to this, because it's a temperature swing adsorption, you have another column where you do the desorption. So you take this clean solvent, you pump it onto your column that is under the desorption process, which means that you're operating at a higher temperature, which was optimized earlier, this 25 and 43 degrees Celsius. And what comes off the column is your product, your pure product with your solvent. So that is diverted into another membrane unit, another separation unit, where you concentrate your product. Okay, that's going to end up in the retentate, and that's going to be your pure crystalline material at the end. And again, what goes through the membrane is your relatively pure solvent that you can recover again. Okay, so here we are applying a separation unit, which is in this case a solid phase extraction in a continuous manner, coupled with a continuous solvent recovery and product waste concentration membrane unit. Okay, and here again, we looked at the E factor and the carbon footprint reduction, and you can see that there is a significant solvent consumption because the solvent waste is represented in orange that you can see here. And then if you apply this in situ solvent recovery, then you end up with 99% less E factor. While when you're looking at the carbon footprint, again, it's a more modest reduction because you still need a lot of energy to operate the thermostat that you need at different temperatures in the system. Okay, and my final slide. Here in the left-hand side, you see this original process, okay, where we extracted one single compound and purified it and recovered the waste. But this can be built into a much larger unit. So again, we are talking about an agricultural waste, which has many valuable compounds. And it was demonstrated that one single compound can be selectively extracted out and concentrated up. But you can do the same thing for many different compounds. So what you see here is the development of a more complex production stream where you have more than one column, and each column is specific to a compound. So let's say in one case we used oleuropein, in the other case we used luteolin, and the third antioxidant. So parallel, you're isolating the different valuable compounds from your waste in this unit operation. So of course the housing will be one in this side and the other side, but you're going to have different columns inside specific for different compounds, and you're going to need more of your membrane units for each of these compounds to be separated one by one. Okay, so now let me just acknowledge my colleagues. So these, all of these works that are presented today, they were done either at the University of Manchester in collaboration with the Technical University of Budapest and here at KAUST. So thanks goes to all my colleagues and students who work on these projects. And again, I'd like to iterate that these different processes that I presented today, many of them can be found in this book that we published recently. This is a textbook and explains the basics of continuous microflow processes, continuous separations, how to combine them, how to do green matrix analysis, among other interesting topics. And I'd like to especially thank my students who contributed to the writing of this textbook. So I think it was a very interesting project that I really enjoyed, and I know that they enjoyed it as well. Putting this together, so this is the result of the pandemic, essentially, when we had time to sit down and actually write this book. And many thanks goes to the Gruyter team for making this happen. Okay, and now thank you for your attention. And I think we still have time for questions, right, Christine?
Yeah, we do indeed have time for questions. So I know that there's no webinar taking place on this account afterwards, so it's okay if we go over. So just wanted to start with that. Thanks for a lovely talk. It was really enjoyable. There were some questions submitted, but if you want to submit more, attendees, feel free to use the Q&A box right now. One housekeeping question there was whether this webinar would be recorded and what would happen with the recording. So I forgot to say that at the beginning. Yes, the webinar was recorded. We've posted past ones, I think both on EFCE's website as well as on De Gruyter's YouTube channel. I'm just going to put a link to the last one there so you know what I'm talking about. And oh, 1 second, did that send correctly? Yep, okay, good. I also put a link to Gyorgy's book in the chat as well as our Twitter page if you wanted to give us a follow. Okay, so the second question that was submitted by João Bergal was actually a two-parter. So it says, Gyorgy, very good work and presentation. 2 questions. Are those membranes presented all produced in-house or are some commercially available? So that's the first one. Maybe I'll let you answer that first and then I'll get to the second question.
Okay, so in these particular examples, we used both in-house made membranes, mainly on polybenzimidazole, and we also applied Duramem membranes, the DM900 that you saw on one of these slides. That was the most open membrane that we applied for the recovery of the cyclodextrin grafted organocatalyst. But just to mention, there are no Duramems anymore. I just received the news from Evonik actually about 2 weeks ago that they is continuing with that particular membrane. So João, if you're interested in open membranes, then Duramem is not available anymore.
Oh no. And then the second question is the fact that it takes some time to establish permeance and rejection in different solvent systems. Any hopes for this to be shortened through modeling with AI or machine learning?
Okay. To establish permeance and rejection in different solvent-solute systems.
Yeah, that's how the question reads.
Takes time. I'm trying to interpret the question. Just a moment.
I guess it would be like, is it possible to model permeance and rejection data in different solvent-solute systems?
We are working on it, and we are not the only one. So I know that there is ongoing work in that area in Germany, actually in Hamburg at the moment, modeling rejection and permeance. We are also working on this area, but it's a very complex system, and I would say that this is still time-consuming.
Still time-consuming. Figuring out the modeling itself is time-consuming. So then
that part as well, and the development. So I think João was initially asking about how long it takes to actually screen these membranes and find the right combination of the substance and the membrane itself to develop these processes. And you still need a lot of know-how. So it's very difficult to predict how these systems perform.
Yeah, I understand. I don't see any other questions in the Q&A box. I don't know if any other attendees wanted to ask something at this moment. I'll give it a few minutes just to see if someone will submit, because last time I did this, I said, oh, it's over, and then there was another question submitted. So I just want to give it a second. Just waiting. Okay, if not, then I'm going to say that that's probably it. I'm not getting another question. Again, I'd like to thank our speaker, Gyorgy, as well as the EFCE and CHISA for partnering with De Gruyter on this webinar series. Again, I'd like to highlight his recently released textbook with us, as well as to mention that we have a large selection of industrial chemistry and chemical engineering books that you can peruse, and that we've hosted past webinars in this series that you can see the recordings of. which are also based, I think, mostly on textbooks. And yeah, perhaps I'll hand it over. I see right now Karen's turned her camera on. Maybe she wants to close out the session. Karen?
Just want to thank everybody. Thank you, Gyorgy. It was a very nice presentation. Thank you, Christine. Thank you, Ines and Willy, for supporting and enabling this workshop. And thank you to the audience.
Yes, and thank you very much for organizing the webinar and everyone who attended it today. Thank you very much.
Thank you.